Hey everyone, and welcome. Today we're tackling a LeetCode problem called lexicographically smallest equivalent string. It sounds a bit formal, but the core idea is pretty neat. We'll break it down step by step, so no worries if it seems tricky at first glance. So what's the deal with this problem? We're given three strings. Let's call the first two S1 and S2, and the third one base string. The strings S1 and S2 are special. They tell us which characters are equivalent. If the character at a certain spot in S1 is, say, A, and the character at the same spot in S2 is C, then A and C are considered equivalent. This idea of equivalence is pretty standard. If A is like B press, then B is like A, and if A is like B press, and B is like C press, then A must also be like C press. This means characters can form groups, or equivalence classes. Our job is to take the base string, and for every character in it, replace that character with the smallest character from its equivalence group. Smallest here means lexicographically smallest. Like A is smaller than B, B smaller than C string, and so on. The goal is to transform the base string into this new string made of the smallest equivalent characters. Let's walk through the first example to make this concrete. We have S1 as Parker, S2 as Morris, and our base string is Parser. The expected output is Makek. First, let's figure out the equivalences from S1 and S2. Comparing character by character, the first characters are P from Parker and M from Morris. So P is equivalent to M from Parker. Second, A and O, so A is equivalent to O. Third, R and R, well R is equivalent to R, no new information there. Fourth, K from Parker and R from Morris, the third R in Morris. So K is equivalent to R, this is interesting. Fifth, E and I, so E is equivalent to I. And sixth, R from Parker, and S from Morris, so R is equivalent to S. Now we need to see how these equivalences chain together. This is where that transitivity rule comes in. So we have these direct links, P with M, A with O, K with R, E with I, and R with S. Let's see what groups these form, always keeping an eye out for the smallest character in each group. The pair P and M form a group. The smallest is M Michus. A and O form another group. Smallest is A group. E and I form a group. Smallest is E. Now for K group R and S, we know K is equivalent to R. We also know R is equivalent to S. Because of transitivity, if K is like R and R is like S, then K must also be like S. So K, R, and S all belong to the same group. The smallest character among K, R, and S is K, R, and S. Now we have our mapping. Any character in the group, M per, maps to M. Any in A, O, maps to A. Any in I, E, maps to A. And any in K, R, and S, maps to A, R, and A. Let's transform parser. P is in the R and A. Caps group, so it becomes M. A is in the R and A, maps to A group, so it becomes A. R is in the K, R, and A's group, so it becomes Kcast. S is also in the K, R, and A's group, so it becomes Kcast. E is in the I, E group, so it becomes E-days. And the final R again becomes Kcast. Putting it all together, we get Makek, which matches the example. Perfect. Okay, how might we approach this from scratch? Our first instinct might be to think of these equivalences as connections in a graph. Each character is a node, and an equivalence is an edge. Then, for every character in our base string, we could start a traversal, like a depth-first search or breadth-first search, to find all characters in its connected component, which is its equivalence group. From that group, we'd pick the lexicographically smallest one. This would work, but imagine if the base string is very long or the groups are large. We'd be doing a lot of graph traversals, which might get too slow. We need something more efficient for finding that smallest representative of each group. So when we talk about groups and finding a representative for each group, a data structure called union find, or disjoint set union, often comes to mind. It's perfect for this kind of problem. The main idea with union find is to efficiently manage a collection of disjoint sets, or in our case, equivalence groups. We can set it up so that the representative or parent of each group is always the lexicographically smallest character within that group. This way, finding the smallest equivalent character becomes really fast. How does union find achieve this? Imagine we have an array, say parent, where parent stores the representative of the character corresponding to index I. Initially, every character is its own representative. A points to A, B points to B, and so on. They are all in their own tiny groups. Now, when we process an equivalence, like C is equivalent to E from S1 and S2, first, we find the current representative for C pairs. Let's say it's C itself. Then, we find the current representative for E. Let's say it's E itself. Since C is smaller than E, we union their groups by making E, the larger representative, point to C, the smaller representative. So, would become CAC. Now, both C and E belong to a group whose smallest member and representative is C. If we later find C is equivalent to A, we'd find C's representative, which is A after this new union, and A's representative, which is A. We'd union them, and A would become the representative of the group containing A, C, and E. This way, the representative of any group is always its smallest member. Alright, here's the Python code that puts this union find idea into practice. It might look a bit dense at first, but we'll go through it piece by piece. Don't worry, the logic is exactly what we just discussed. First up, we initialize our parent array. Since we're dealing with lowercase English letters, there are 26 of them. We can map A to 0, B to 1, and so on, up to Z as 25. List, range, 26, creates a list like 0, 1, 2, 25. This means, initially, each character, represented by its number, is its own parent, its own representative. So, A points to A, B to B, etc. Next, we have the find function. This function takes a character's numeric value, let's call it I, and figures out the ultimate representative of its group. If parent is I itself, it means I is the representative, so we return it. Otherwise, I points to something else. We recursively call find on what parent is points to. That little line parent I equals find parent I is a neat trick called path compression. It makes future lookups faster by making I point directly to the ultimate representative once we find it. It's like creating a shortcut. Then there's the union function. It takes two characters' numeric values I and j. First, it finds the representative for i's group, let's call it root I. Then, it finds the representative for j's group, root j. If these roots are already the same, the characters are already in the same group, so we do nothing. If they are different, we need to merge the groups. We compare root I and root j. Whichever one is lexicographically smaller becomes the new representative for the combined group, so the parent of the larger root is set to be the smaller root. This ensures our smallest character is the representative rule. Now, we loop through the input strings S1 and S2 for each pair of characters at the same position. We convert them to their numeric values, 0 for A, 1 for B, etc. Let's call these SHA1 val and SHA2 val. Then, we simply call our union function with these two values. This processes all the given equivalences and builds up our parent array to correctly reflect the groups and their smallest representatives. Finally, we construct our result string. We iterate through each character in the base string. For each character, let's call it char base. We convert it to its numeric value, SHA val. We call find with SHA val to get the numeric value of its group's smallest representative, root val. Then, we convert root val back to a character by adding the numeric value of A and append it to a list we're calling result chars. After checking all characters in base string, we join all the characters in result chars to form our final answer string. And that's it. So how efficient is this union find approach? For building the parent array by processing S1 and S2, each union operation, thanks to path compression and union by rank size, though we used a simpler union by smaller value here, which is fine for fixed C, is very fast, almost constant time on average. Let's say L is the length of S1. This part takes roughly L times that near constant time. For constructing the result string from base string, length M, each find operation is also very fast, so this is about M times near constant time. The C is just the size of our alphabet, 26. That near constant time is often written using alpha, the inverse Ackermann function, which grows incredibly slowly. For all practical purposes with only 26 elements, it's a very small constant, so the total time complexity is effectively linear, something like order L plus M. For space, we mainly use the parent array, which has a fixed size of 26 for the alphabet, so that's constant space, or order 1. This is really good. So, to recap the main ideas, The problem is about finding the lexicographically smallest character in an equivalence group for each character in a given string. These equivalences, reflexive, symmetric, transitive, naturally form groups or disjoint sets of characters. The union-find data structure is a perfect fit for managing these groups efficiently. The core strategy was to make sure that when we union two groups, the representative of the new, combined group was the lexicographically smaller of the two original representatives. This allowed us to quickly find the smallest character for any group using the find operation. The result is a solution that's both elegant and efficient in terms of time and space. Hope that breakdown made sense and helped you understand the problem and the union-find solution. If it did, feel free to hit the like button, subscribe for more LeetCode explanations, or drop a comment if you have any questions or other ways to solve it. And hey, if you're feeling extra generous, there's always the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one.